All right, so now we're going to look at some classic mediation examples. So the first one is on work team performance. So we have the model here. This is a case 2, according to the book. So what we have here is dysfunctional behavior. And this is how often a worker engages in weakening of others' work somehow. So I guess that would be if Bengt undermines what I say when he talks, something like that. And then negtone, which is negative effects about the work, if you have negative effects associated to your work and your workplace. And then the outcome is performance or work efficiency. So this is kind of a common outcome that employers are interested in. How can they increase the efficiency? What should they change? And then we also have the neg-exp, which is the non-verbal ability to express negative emotions. So the non-verbal ability, if you can show how you feel, basically, without saying anything. And then we have M-said here in this case. Let me just see that. Which is then, of course, negtones times neg-exp. So if you have negative effects, and if you are able to express them non-verbally. So one story here could be, for example, that if you are treating your workers and undermining their work, then you might end up having a lot of negative emotions associated to your workplace because you have this bad environment. And that might, of course, affect your work efficiency or performance. And also then, if you have a low ability to express how you feel non-verbally, so no one can see that you're feeling bad about this, then it's hard for anyone to regulate this. So it might be even worse for you to have negative effects about your workplace if you're unable to express them, for example. So this could be one reason to look at this. So how would we set this up then? So it's nothing new except that we have to create this interaction variable. And when we want to define something, we have already done this in the first one. We just use the define statement and we say we want to call M-said is negtone, so the negative effects, times neg-exp, the non-verbal ability to express negative emotions. And then what we will use throughout when we do mediation analysis with the maximum likelihood estimator, we will also use Bayes later, but now when we're in the maximum likelihood framework, we will use the bootstraps. And that's, we will use it for the confidence intervals, and that is to be able to capture the non-symmetry and the skewness that we kind of anticipate in the sampling distribution of especially the indirect effects. So we will have that kind of as a default. We will always use the bootstrap confidence interval when we do mediation analysis with the maximum likelihood estimator. And we will see why in a couple of slides. And then we just put up our model. We have 2 regressions here. We have the regression of the outcome on the negative effects, the dysfunctionality, or the exposure in this case, the nonverbal ability to express negative emotions, and the interaction between these two. And then the mediator is only regressed on the exposure. On the exposure dysfunctional behavior. And then we come to the model indirect command, which is the way that we get the indirect and direct effects for these models. And there's some things to think about here. There's a lot of information here and a lot of things that are important. So the first thing I want you to note is the order here. And that's why Bengt gave you the cheat sheet. What's that? The slide, I forget the number now, but the slide where all these definitions of what order it should be in what case. So you can keep track of this. But I will go through it. So what you have is, first of all, we're going to use the mod option because we have moderated mediation. So we're going to use mod rather than ind. So the mod option. And the order is the outcome, and then the option mod, and then the mediator negtone, and then the moderator neg-exp. And we have some values in parentheses after that, but let's skip that. So just the order. So the outcome, mod, mediator, moderator, then the interaction verbal, M-said, and finally the exposure dysfunc, which also has values in parentheses afterwards. So let's look at the values within parentheses now when we know the order. And you don't have to remember this order. You have this order on the slider. So the first values here are neg-exp, so the moderator, and then we have from -4 to 0.6 with the increment 0.1. So this kind of very much resembles what we did with the loop command before. So this is exactly what we're doing here. We want to see the indirect and the direct effects for different values of the moderator, right? Because it will change as a function of the moderator. That's why we have the moderator. So this will give us a plot that gives us the effect as a function of the moderator over this, for these values, from minus 0.4 to 0.6, and the increment just gives the smoothness of the plot, of how many points we're estimating. And this corresponds, in this case, to the 20th and the 80th percentile of the moderator. And the moderator, in this case, was the nonverbal ability to express negative emotions. And then the values within parentheses after the exposure, that corresponds to the x0 and x1, right? Because we have to say for what shift in the exposure is a continuous variable. So for what shift in the exposure do we want to see these effects? So in this case, we will go from the mean to 1 standard deviation above the mean. So you write the highest value first, and then, so this is an increase from the mean to 1 standard deviation above the mean. If this would have been a binary exposure, we wouldn't have to write anything, because the default shift is from 0 to 1, which is a binary exposure. Right? You either was given the treatment or you didn't have the treatment. But in this case, we have to choose for what values we want to evaluate the effect. And then again, we use the C interval within parentheses bootstrap here to use the bootstrap samples for the confidence intervals. And then the plot here, I can just say here, we ask for type equals plot 3 in the plot command, we get these kinds of plots. And here we have exactly this. So you can see here on the x-axis we have neg x, which is the moderator. And this plot starts at minus 0.4 and ends at 0.6. And the smoothness of this corresponds to this increment 0.1. So this corresponds to the value in parentheses after the moderator that we saw on the previous slide. So these values. And the line in the middle is the point estimate, and these bands are the confidence interval, the 95% confidence interval. And we have then the indirect effect now on the y-axis. So we can see how the indirect effect of the dysfunctional behavior mediated through negative effects about work, the indirect effect on the work efficiency here as a function of the moderator nonverbal ability to express negative emotions. So actually we see that when the nonverbal ability increases, the negative effect increases, right? Because this is negative values that becomes larger and larger. So the negative effect increases. It's a lot of negatives back and forth there. So as the nonverbal ability to express negative emotions increase, the negative effect of dysfunctional behavior mediated by negative emotions on the work efficiency becomes larger. So the negative effect becomes larger. Or you could say, for individuals with a high nonverbal ability, it's worse to have negative effects. So this is kind of the opposite what I suggested with my story. It's actually the other way around. If you have a high ability to express your emotions, it's even worse to have negative effects about work. So maybe it's some kind of self-fulfilling prophecy or something. You show everyone that you're feeling bad, so and then everyone treats you like you're a grumpy person, so your work efficiency becomes even worse. So that's what we see here. As the moderator increases, the negative effect increases as well. And you can see here that it's significant for values larger than minus 0.15, for example, where the confidence interval does not cover 0. So one thing you have to think about here, when you specify a model like this in Mplus, you estimate both models at the same time, both regressions at the same time, which will give you 2 degrees of freedom that you don't want, in a sense. And this will give you a very bad chi-square fit. And if we go back to the model diagram here, essentially what we have left out here is the correlation between the residual and the moderator, and the residual and the interaction variable here.
Do you mind? We asked that questions be asked at the question and answer session, unless it's totally confusing.
Yeah.
What is missing?
No, the moderator here is the negative nonverbal ability to express negative emotion. That's measured. Okay, let's get back to it during the questions and answer questions, I guess, so we don't. No, it is correct.
It is correct.
Yeah.
Okay, so you're gonna.
Yeah, it's correct. It's correct. I know that. No, but I mean, this different cases. It wasn't that many years ago that I understood this. I still kind of recall it's kind of difficult to get all these different cases. It took a long time for me to kind of internalize how they make sense. But hopefully it will unfold. We'll see. Where were I? Yeah, okay, so we left out these two covariances here between these two. And that will give you a bad model fit here. And this is nothing that you should bother about, really. But if you want to aesthetically make this output look better, you can saturate this model by allowing this covariance, by mentioning this statement in the model command. And this will not affect any of the other estimates, not the point estimates or the standard error estimates of the rest of the model. So this is purely aesthetical. But maybe you have to send this output to some colleague that is not as good at statistics that you are. So that person might get very worried about this bad fit and everything, and you don't have time to explain because you have to go to courses like this. All right, so another case 3, which Bengt mentioned, is a case which we should always kind of consider when we have a simple mediation model. We have an exposure, mediator, and an outcome. Is the interaction between the exposure and the mediator. So mx here. And as you can see, as Bengt already mentioned, you can see that the values of x in this case affects the indirect and direct effect. So in the indirect effect, it's the x1 value, and in the direct effect, it's the x0 value. But it's also the shift. So like Bengt said, it doesn't only matter how large this shift is. So from 0 to 1 or from 1 to 2, that's a shift of 1 unit, right? But actual value, 0 or 1 or 1 or 2, matters here for the effect. And the reason why we should always increase this, I think Van der Vele wrote a nice quote in his book, Exploration in Causality, which I will give you some seconds to read this, and then I will try to summarize it. So essentially what he says here is that even though you might be tempted, like Bengt said, to exclude this kind of interaction if it's not significant, maybe we should include it or keep it anyway unless it doesn't change the effects, the indirect and direct effect, if we remove it. And that's because usually it takes huge samples to find significant interactions. But that doesn't mean that there is no interaction. So that might still be very important for the dynamics of this mediation, right? So to really capture how this works, like for example with the baseline aggression thing, it makes a lot of sense that it would matter if you have a high baseline aggression, if we talk about if we can change your aggressive behavior. And that might, of course, interact. So kind of as a default, we should include it and keep it unless it doesn't affect the results. So how do we do it then? Well, it's very similar to the setup we have previous. We create this interaction variable in the defined statement. So we create mx, which is the product of the mediator and the exposure. And then we just do the model. So y in this case is regressed also on the interaction besides the mediator and the exposure. And in the model indirect command now, again, I refer back to the sheet where you have all these different kinds. This is the case 3. We have the outcome and then the mod option because it's still a moderated mediation model. But then we have the mediator and then straight to the interaction variable because we don't have any external moderator here, right? The exposure is both the exposure and the moderator, essentially. So we don't include that, so we go straight for the interaction variable mx in the order here and end up with the exposure. And again now, after the exposure, if it is a continuous variable, we have to say for what shift in the exposure we want to see these effects. So this is from the mean 5 to, I think, one standard deviation above 5, 7 in this case. All right, so how would you then simulate on this? I mean, why would we want to simulate models with moderated mediation? Well, maybe to see what it takes to get a significant interaction effect. We might be interested in the interaction effect, right? So we might want to design a study where we know that we have power to detect significant interaction if there is one. So you can simulate this in Mplus, of course, and see what it would take. How large sample would you need to be able to find a significant interaction with some probability? And to do this, you kind of have to learn a trick. You have to realize that you can write the interaction as a random slope. So if we look at these three, so now it's x and z here, moderation. So the trick here is that we can write the slope of x with a subscript I. So if you look at the regression of M here, we can write it with the subset I, where the subset refers to this function. So each individual's slope of x is this linear deterministic function of z. So if you would insert now 32 into 31, so this expression instead of this gamma here, put this expression in, you have x times gamma 1, and then x times z gamma 3. So you have these two terms. So if you realize that you can write it in this way, then this is an excellent trick which you have to use to generate this data in Mplus. I don't hear you. Sorry. Here? It's here. So it's measured at baseline. So this could be baseline aggression. This could be aggression at grade 5, and this could be high school dropout, for example. I will have an example of that later. OK, so if you see this, you understand that you can actually view the interaction variable as a kind of a random slope. And how would you generate this then? Well, OK, I'll just repeat this slide one more time from the beginning. So what we have here is we have x, z, so interaction between these two. And this affects only the mediator. So only the mediator has the interaction effect. So it's only in the mediator equation that we have to take this into account somehow. And the way we do it is to set a subscript I on the slope of x, saying that each individual have their own treatment effect, their own slope of the treatment or exposure, their own slope of x. And this slope is a deterministic function, a linear function of z, which is the moderator. So if you would put this expression here, gamma 1 plus gamma 3 zi, and substitute this gamma 1i here with this expression, you would have parentheses around this, and then gamma 1, gamma 3 z, end parenthesis, and then xi. So if you would multiply that in, then you would have the term xi times gamma 1 and xi times this term, which would correspond to the interaction equation, the regression with interaction. For each individual. Yeah. And the way you generate this data then is, so I'm not going to go through all of this. I'm just going to say really quickly that you can specify how many replications you want to do in a simulation study, 500 in this case, and you can say the data if you want to for each replication. And the way you then specify the random slope is you use this statement. So in the regression of M regressed on X, so the mediator on the exposure, we're going to have the random slope, gamma 1. So gamma 1 is the name of this random slope. And the random slope is indicated by this vertical bar here. So M on X will have a random slope, gamma 1. And then the following three lines says that gamma 1 will have an intercept of 0.3. And it will be a function of Z, where the slope of Z is 0.2. We simulate data here, so we can decide exactly how to generate this. And finally, we set the residual variance of gamma 1 to 0. So it's a deterministic. We don't have any residual term here. It will be this deterministic function that we talked about. And that's how you go about it. I'll just briefly show you the output, because it differs a bit from when you don't do a simulation study, when you just do analysis of a data set. You have now more columns that you have to take into account. The first one is similar for us. So for example, gamma 1 on Z, the population value, that's the true value, something that we have to specify. How did we generate this data? So the true value was 0.2, which I specified before. And the average, because these results are the summaries of the 500 replications that we did. So it's the summaries of these. So the average of all the 500 point estimates for this parameter were 0.201, which is very close to 0.20. So it's a good, on average, it did really well. And then we had the standard deviation, which is the empirical standard deviation of all these estimates. So you just calculate the standard deviation of these 500 point estimates. And that should correspond to the standard error average, right? Because the standard error is the estimate that we get for each of these replications that should correspond to the empirical standard deviation. So if everything goes well, then these should be comparable. If the standard error estimate is able to capture the true variability in this estimate, then these two should be close, and they are. And then we have 3 columns in addition to this, which are the MSE, mean squared error, which is kind of a combination of the bias and the variance of this. So it's kind of a precision measure. And then we have the 95% coverage, which is the proportion of confidence intervals that covered the true value. And this corresponds to the frequentistic definition of a confidence interval. If we would repeat this over and over, then in 95% of the cases, the confidence interval would cover the true value, right? So the goal here is 95. So this is actually spot on, which is really good. And finally, we have the percentage of significant coefficient. So the proportion of confidence intervals that did not cover 0, because that would be a significant effect. It's significantly different from 0. In this case, we can see that 74.4% of these effects were significant. And we can see from some others here, we have only 60% or 75%, which would indicate that the sample size we used, 400, is not enough to get the power that we would like. Usually we talk about power above 0.8 or 80% as good power. So in this case, we would have to increase the number of participants. And then you can really see that it takes a lot to get significant interactions here and to get these models to be all significant. And if you don't have anything to add, Bengt, I think you can talk about sensitivity analysis.
I don't know anything about it.
Oh, it's too bad.
Just one quick question. Where do you see gamma 1 on Z in the diagram? Sorry.
Gamma 1 on Z is this gamma 3.
Yeah.
So that's this one. So gamma 1 on Z, this is the critical one. You know, this is lower than 0.8, as Morten mentioned. And that is the one that we often, interactions like that we often find insignificant. So it's this one that we're talking about. So the first row in the output corresponds to that.